All right, welcome to Talk Data to me with myself, Craig Stewart. Really interesting episode I've got in the works for you today. I'm speaking to one of our Data Fest speakers, Dr. Dineo Tsabedze. Dineo, thanks so much for joining me. So I think everyone I'll get Dineo to give us a bit of an introduction, but aside from having an actual PhD, Dineo is also a medical doctor in the field of nuclear medicine. Dineo, thank you so much for joining us. Really looking forward to having this chat with you.
Thank you so much, Craig, for the invitation. And I'm looking forward to having a lovely conversation with you.
Yeah, likewise. All right,
Mm.
Dineo, let's maybe start just giving everybody a bit of insight into your background. I think people watching are very familiar with our speakers coming from banks and retailers and telcos and things like that, not necessarily from a medical background. But we'll get into the detail of why you're on Talk Data to Me and also Data Fest as well. But maybe you could just talk us through your journey. I mean, Mrs. South Africa, top 10 finalist as well,
Thank you,
which
Craig.
is fantastic. But obviously, medical doctor in the field of nuclear medicine. Tell us a bit about Dineo.
Okay, so I am Dineo, and I was born and raised in Durban. And just to kind of connect my journey as a child with where I am right now. So what happened was back in the days when I was still probably like 7 or 8 years old, um, I was fortunate enough to be in a room filled with computers, and these were computers made using recycled material. So at that time, my uncle was a school principal, and he managed to find a few donors that were actually able to donate a couple of computers to one of the public schools where he was teaching. So seeing that, this is a fascinating box, I didn't know anything about it. As you can imagine, at that time, there was no internet. I think we just had exposure to televisions. So I was quite curious about how a computer functions. I didn't know much about it, and I spent a lot of time working on the computer. I cannot even remember what is it that I was doing, but essentially for like a few months, I never left my bedroom. I was always busy pressing and doing things until this one time where by mistake, I'm not sure what actually happened, but I uninstalled the operating system and I panicked. I panicked. I thought, this is it. This is the end of it all. This computer will never function again. So I sat there without telling anyone, struggling. And to my surprise, eventually I was able to reinstall it back without even using a CD or at that time, actually, we're using floppy disks.
Mm.
And I think that kind of cemented my relationships with computers. So since then, I've always wanted to know more. And I felt like I am in a way at an advantage or in a position where I'm ready really to explore anything that computers may actually be able to execute. So since then, I've just been really fascinated. I also do statistics for my students or any researchers that I'm working with, and I love it. I mean, I can stay up until 3 a.m.
Yeah.
just running different statistical formulas just to see what kind of output are we getting from the data that we're currently mining. So realizing that, then I decided to also specialize in nuclear medicine because I knew that I wanted to be a specialist. But the interesting part is that at that time, I didn't actually know what nuclear medicine was about. And what I did was, while I was actually working as an intern in Durban, I visited Joburg and I spent a week in the nuclear medicine department trying to learn more about what they do. And to my surprise, when I walked in, there were like computers everywhere. And these computers are obviously used to process the images that we acquire from the patient. So since then, I was sold. I was like, this is it. This is what I want to do. I'm never turning back. So then I completed my specialty in nuclear medicine. And then I decided to also pursue a PhD. And as you can imagine, because I'm a nuclear physician, I wanted to focus on nuclear medicine and do a PhD that involved AI, where we use AI to interpret cardiovascular images or images of the heart. And unfortunately, at that time, when I started the PhD, we didn't really have a robust data set in the nuclear medicine department. And most of the images that we had actually stored them as JPEGs instead of and the actual raw images where you can actually even look at the pixels. So then I ended up visiting other departments, and luckily for me, one of the cardiology departments in the hospital where I was working actually had a robust database where they've been collecting patient data since 1999. So I was fortunate enough that I was able to mine that data, and I then used it to predict the risk of in-hospital mortality on all the patients that we're presenting with heart failure. So I trained 7 machine learning algorithms, and luckily enough for me, the project was a success. So I managed to publish my papers, and here we are.
Right, perfect. Great introduction. Thank you very much. I think you didn't know what nuclear medicine was. I think pretty much 100% of the people
Mm,
watching this don't know what nuclear medicine is and what a nuclear physician does.
mm,
Obviously, you've told me about it, but maybe you can just go into a little bit of detail
mm.
about what nuclear medicine is, and then we'll get into that sort of research and sort of the work that you've done around the data and the
Mm.
predictive analytics.
Okay, wonderful. So nuclear medicine falls within the same fraternity as radiology, meaning that we perform scans. And more recently, now with nuclear medicine, we're actually able to treat whatever that we're able to visualize on the scan. So we use traces of radiation. So if you think back to the periodic table that you're exposed to back in high school, remember that there were a whole lot of elements there. So there are some elements there that are unstable. And when they decay, or meaning that they lose energy, they're actually able to release radiation, which is basically energy in motion. So
Yeah.
what we do is we take those atoms that appear, or elements that appear on the periodic table, we actually manipulate them, and then we're able to introduce them into the human body. So either intravenously through the veins, or the patient would inhale the radiation depending on the nature of the study that we're conducting. And then we're able to then use special cameras to then track the distribution or the movement of that radiation in the body. And then based on the pattern that we're able to see, then we're actually able to inform the doctors about the functionality of different organs in the body. For example, if a doctor was concerned about the functioning of the heart, you have an option of sending a patient for a CT scan. I know a lot of people are aware
Yeah.
of CT scans. So the CT scan will actually visualize the vessel and tell you, there's a vessel there. We're seeing a blockage. It's possibly 70% blockage. Whereas with us, with nuclear medicine, we'll actually tell you about the functionality at that site of blockage. Is the blood actually flowing? If you're to estimate how much blood is being sent to that organ. So basically for us, we focus more on physiological function,
Mhm.
whereas radiology would focus on the anatomical detail.
All right, perfect. All right, so let's then step into kind of following that. You really have your PhD in data around predicting heart disease, right? And I'd
Mhm.
assume there that you've got, through the nuclear medicine as well, sort of
Mhm.
like
Mm.
a benchmark level of what normal should be, and then that's your data set that then you can see if there's
Mhm.
any variations
So,
to that. Let's maybe talk
mhm.
a little bit about how you train
Mm.
the models, and I guess also some of the challenges that you've got. You said you had
Mm.
patient data from 1999. Obviously that's relatively old, is maybe not
Mm.
collected in the best way. Maybe walk us through some of the challenges that you had, kind of getting to the point where you were confident in the accuracy, because you're not dealing with this is the next product a customer's going to buy. This is life or
Mhm.
death. It's got to be very,
Oh,
very
yes,
accurate.
yes, yes,
So
yes.
it's really, really important. Anybody
Mhm.
else watching thinking that their data quality is causing an issue, this is even bigger. But maybe just talk us through that. Like, where did you get the data from? What are some of the challenges that you've got, and how are you sort of, I guess, solving some of those problems?
Okay, so I used data from the Division of Cardiology at Charlotte Maxeke Academic Hospital, which is a state-owned hospital. And as you can imagine, at that time, no one was thinking along the lines of archiving data. But luckily, the professors that were there, they actually thought about it back in the days in 1999. So the data that I mined was actually for patients with heart failure, meaning that the heart is no longer pumping enough blood to supply the needs of the body. So when I started mining the data set, I had about 26,000 patients with various heart conditions. So everyone had a heart problem. And then from that data, I then had to focus on a niche, because whenever you train model, you have to kind of bring it down to a specific population, so that you're actually able to, have an output that will make sense. So then I decided to just zone in specifically on, on those patients with heart failure marked by an ejection fraction less than 50%. So I had a diagnosis, or a column on my data collection sheet with a specific diagnosis. In addition to that, I needed objective evidence that the patient actually had heart failure. So there would be the left ventricular ejection fraction, which reflects the amount of blood being pumped out by the heart, in a percentage format. So I then zoned in on patients with an ejection fraction that is less than 50%. So unfortunately, when I looked at the data set, I started with like 3,000 patients with heart failure. And then to my surprise, only 500 had objective evidence that, they actually had
Yeah.
heart failure. And unfortunately, I then had to just focus on those, because I tried to go back to the archive to retrieve the data, to see if I can, increase my sample size. I mean, we even tried to add synthetic values, but then we also felt with the synthetic values, one needs to really understand where they're coming from, because
Yeah.
all they really do is they would maybe take the mean and the median of all the numerical features. So then we decided against it. We said, let's just take the data as is. Unfortunately, the sample size is not what we're looking for, but the one thing that we're confident of is that the data is actually credible. The population that I selected actually had heart failure. So then I then used the traditional statistical methods such as logistic regression to analyze the data. So basically now what we're doing is we're looking for predictors of mortality or predictors of death, because
Mhm.
before the patient leaves the hospital, we know who died while in the hospital, and we know who was discharged alive. So that was my output feature. So what ended up happening is that I used like I said, the traditional statistical method. And in addition to that, I used machine learning. And then before deciding, because you can imagine there's like a wide array of algorithms that are out there. So I ended up conducting a systematic review. And then I looked at all the literature available showing us all the different algorithms that have been used before to predict heart failure. So I ended up resorting to selecting just 7 that were commonly reported in literature.
Yeah.
And the rationale for that was that I also wanted, a basis for me to be comparing what I've done versus what's already out there in literature. So then that's exactly what I did. I trained the 7 machine learning algorithm. Basically, they were all classification algorithms. Yeah, so I won't mention all of them. And then we actually found that, they did reasonably well because the data was actually credible. So I was actually able, like I said, to publish my work, with the next step now being us creating a risk predictor that we can upload online, so that if doctors see a patient with heart failure, they know when to refer them. For example, if the risk of mortality is high, then the patient should be referred straight to a hospital equipped with cardiology services. Whereas with the probabilities on the lower side, then under those circumstances, the patient can be seen in the general medical wards. But like I said, the main challenge for me was the credibility of the data. I spent close to a year cleaning the data more than anything, just 1 year,
Wow.
rather than focusing on, yes, that's how terrible the data
Yeah.
was. But I mean, I really tried. I even had to hire people to help me, medical interns, to help me verify the data, go back to some of the written records to see, can we cross-check or even add some of the fields that were empty, but still we ended up with only 500 credible patients. So that's what we worked with. And then I think for me, the important thing is to maybe understand, how did we get there? I mean, these are legal documents, it's patient data.
Mhm.
Why did we find ourselves in the predicament? Number one, the system that we were using for collecting the data, because I also maybe for like a few months actually worked in the division of cardiology, recapturing this data and capturing some of it.
Wow.
So I
Yeah.
had firsthand experience, and it was so outdated and slow. I think just capturing one patient will take you 25 minutes. Now you can imagine the doctors rotating in cardiology, they have other responsibilities as well. For example, they find that they have exams, they have tutorials, they have to teach, they have to do night calls. So imagine now you've admitted 10 or 20 patients, and it'll take you 20 to 30 minutes to capture data of one patient. So it's quite cumbersome. And I felt that maybe if we had a better system, we wouldn't have been in a situation where some people would capture just the bare minimum and leave maybe some of the details, which for me I felt were relevant. Then secondly, I believe that not having a dedicated data team who are actually stationed in the department and their sole
Yeah.
mandate is to collect the data was actually one of the contributing factors that led us to experiencing challenges when it came to the credibility of the data.
Yeah. So I think, I mean, that's sort of the question that comes to mind is obviously very valuable prediction that you're coming up with. This is obviously, preventing death, preventing heart failure or treating heart failure up front. You know about it, all the
Mm-hmm.
indicators are there within the patient. So the use case is a very important use case. How has
Mm-hmm.
it changed the approach to data collection within the hospital, if any? You obviously talk about having like a data team to go and actually, help with the clinicians and actually collect the data as they go, rather than,
Mm-hmm.
the doctor, the clinician, etc., collecting it. Has it made any sort of change in terms of the structure and the data collection and the data quality within the hospital?
Absolutely. I ended up voicing all the challenges that I faced with my PhD supervisors as well as the head of department in the division of cardiology. And since then, what they've done is they now have a dedicated team of individuals that focus primarily on keeping track of the data, reviewing it after the collection to make sure that all the necessary fields have been captured. There's even a software engineer who actually now is an intern. Yes, he works in
Brilliant.
the
Yeah.
division of cardiology, and what he's actually trying to do now is to see how can they improve the system without actually losing the data or affecting its integrity. Because if I remember correctly, we're using SQL, structured query
Mm.
language, to
Yeah.
actually save this data in tables. And the important thing now was to say, because it's such a robust data set, it's lots and lot of tables. As you can imagine, there's a table just for the age, the gender, what the doctor saw on clinical examination, what the history entailed, the imaging findings, such as the echocardiogram, which is basically the ultrasound of the heart, blood work, medication. So it's quite a
Yeah.
lengthy data set if you think about it. So it was very important for us to say, before we even export this data, do we have an idea and understanding of how all these columns are linked, especially taking into account that there could be errors here and there. So we now have a dedicated data manager as well as a software engineer, I can
Yeah.
call him that, working on the project to ensure that we don't lose out on all this data, because it wouldn't make sense. I'm sure you can imagine, agree with me, Craig, in saying, just saying we are deleting or forgetting about what we
Yeah.
did and we're just moving forward. So we wanted to make sure that we take whatever that we can that we feel is credible.
Mm-hmm. And let's talk then maybe about patient outcomes in this environment. What have you seen
Mm,
from a, I guess, a reduction in, deaths, etc., survival rates, improved patient
mm.
outcomes, from all this work that you're doing, this predictive model that you've come up with, what have you seen, from a patient perspective in terms of improvements?
Okay, so unfortunately for me, or well, maybe fortunately,
Yeah.
I ended up leaving Charlotte Maxeke. I was appointed as the head of department at Sifako Makato Health Sciences University, which is SMU. So when I took over as
Mm.
the head of department, there were just a lot of things that I needed to take care of, and I'm still busy. And I
Yeah.
never was actually in a position to have enough time to go back to Johannesburg and Charlotte and actually say, now that we've done this work, where are we? But with that being said, I'm still busy on a project with one of my PhD supervisors, where we now say, looking at the patients between 1999 and I think it was 1999 and 2018. That's exactly what I did. So now we're saying, if we then now incorporate data from 2018 up until 2024, what else can
Yeah.
we see? So we're still busy with that. We're also trying
Mm.
to see, are we able to predict rehospitalization using the same data set? So we're still busy with that project. It's currently ongoing.
Yeah. Oh, good stuff. I mean, it's fantastic to see,
Mm,
data in use in such a, I think data for good, I think is the term. Like
absolutely.
data and AI for good. What do you see maybe just sort of looking forward into the future, the role of data and AI in medicine, sort of generally, sort of, not just specifically in the heart disease environment? How do you see it really making a difference?
Okay, so for me, I think it's a convention that the moment we're actually able to integrate genomic data, where you look at the DNA of a patient with the clinical data, we'll be able to predict more specific outcomes that are unique to each patient, which is in line with precision medicine. So where I'm going with this is that currently most departments are working in silo. For example, in cardiology, they're focusing on their niche, the clinical data of patient with heart disease, but they don't really have maybe collaborative efforts with, say, for example, another department that focuses on imaging, like nuclear medicine, to say the same patient that we saw in the clinic in the cardiology department, we also referred to nuclear medicine. What were the imaging findings? When now you start looking at the images and you say, can we actually use convolutional neural networks or deep learning to analyze the images and then integrate the data with the clinical data and the genomic data. So at the moment we're actually able to to integrate such data, I really feel we'd be able to show or make groundbreaking discoveries, especially when it comes to therapeutic advances. Where now, if for example the patient is at high risk of death, you're actually able to say what is the main predictor? Is it the genomic makeup, or is it now perhaps environmental factors like smoking or alcohol, then you'll be able to treat the underlying cause.
Yeah, I think that's the question that comes to mind with me, like talking about the genomic data is, can you see who has a greater propensity to have heart failure, all those sorts of things, and then, do it at a very young age. And, because I think there's a lot of, sadly, there's a lot of people out there that, smoke and drink and all that sort of thing, and they will live a very long life, healthy, all that sort of thing. And there's other people that, maybe don't, smoke or drink, and maybe it's just a diet type thing, but they will then get, that sort of heart disease, etc. Is it a way to kind of really bring that process and the sort of discovery, as you say, so much further forward to say, look, you are at high risk of heart failure in the future, therefore don't do X, Y, Z. I mean, I've got, you can give the recommendation, right? Whether someone does it or not is up to them.
Absolutely, because now what you're tapping into is prevention, really primary prevention, where you don't wait for a patient or an individual to actually have symptoms. So you can actually, at a very young age, say, this is your genomic makeup. You have a mutation here or an abnormality in your genes. Therefore, these are the recommendations in terms of how you should live your life. Avoid smoking, avoid a fatty diet or fatty meals, avoid, or rather, we encourage physical activity. So I think for me, that will be really, really groundbreaking, where you can actually prevent the disease rather than waiting for a patient to actually be affected by the condition and say, oh, now that you have heart failure, for us to prevent the risk of mortality or death, this is what you need to do. That's already like secondary prevention. It's a little bit too late by then.
Yeah, so the reversal is much harder than just the prevention in the first place.
Absolutely, absolutely. So prevention is better than cure.
Yeah, perfect. Dineo, this has been fascinating. I've learned so much. Yeah, really, really interesting. I'm really looking forward to meeting you and seeing you present at DataFest in Cape Town in November.
Thank you so much. I'm looking forward to it, especially also with collaborating perhaps with other data scientists and other industries, understanding what is it that they're doing and seeing how we can, as a collective, come up with predictive models that are not just, for the sake of, publishing, because I feel for me, that's what I've been focusing, publishing, but we're actually able to transform how people actually live, their longevity, the decisions that they make based on the risk stratification that we've embarked on.
Yeah, perfect. All right. Well, those that are watching that are going to be at DataFest as well and think you've got a data set that you can use with Dineo to collaborate on, actually augmenting that data set and getting better insights, please do that. But again, thank you, Dineo. It's been great chatting to you.
Thank you so much, Craig, and goodbye to everyone that was listening.
Yeah,
thank you.
Okay. All right, perfect. It was good.